Hello friends, myself Dr. Nandakumar Raubavale from College of Engineering Ambazogai is going to deal with Applied Thermodynamics 2. This is our 6th lecture. In previous lecture, we have discussed about the refrigerants, physical properties of refrigerant, qualities of ideal refrigerant, selection of refrigerant, pH diagram for the properties of refrigerant, advantages and disadvantages of vapor compression refrigeration system. So now today we are going to discuss about the chlorofluorocarbons, TS diagram, pH diagram. Yesterday we committed a certain mistake in previous lecture. So instead of chlorofluorocarbons, I called as a hydrochlorofluorocarbons are harmful to ozone layer. So once again we will have a focus on chlorofluorocarbons, as well as in TS diagram the pressure lines I explained wrongly, and pH diagram was correct. Only the thing is the unit of entropy was spelled wrong. Now the components of vapor compression refrigeration system we will see. Then what is a compressor and what is function of compressor, what happens in the compressor, then condenser, expansion device, evaporator, and working of vapor compression refrigeration system. Finally, we will find out the coefficient of performance of vapor compression refrigeration system. So, chlorofluorocarbons, CFCs in short, are certain chemicals which are harmful to ozone layer. What is this ozone layer? If we see, this is the earth, and around this earth there is a one layer of oxygen, that is O3. This layer, which is around the earth or which envelops this complete earth, protects earth from the ultraviolet radiations coming from sun. So these ultraviolet radiations which come on the earth, if are coming directly on the earth, are harmful to the all living beings, maybe plants, maybe human beings, maybe animals or microorganisms. This is going to harm. So if this ultraviolet radiations, if a person is exposed to ultraviolet radiations, then a human beings are suffering from skin diseases as well as eye disease or blindness is going to occur. So this ozone layer plays very important role. So this ozone layer prohibits these ultraviolet radiations from entry into the earth environment. And now these chlorofluorocarbons are having effect over this ozone layer. So these chlorofluorocarbons, CFCs, are going to affect this ozone layer which is around earth surface. And if this ozone layer gets depleted, if it gets destroyed, then the ultraviolet radiations of sun directly come on the earth. So first time in 1983 or 85, the British scientists found that there is a hole to the ozone layer in the Antarctica region. And many of the people are suffering from this ultraviolet radiation. So it is banned by universal community, by the UN, United Nations of Organization, UNO, to use these chlorofluorocarbons which are harmful to ozone layer. So gradually the use of these chlorofluorocarbons is reduced. So because of environmental concerns, the use of CFCs is has been banned and it is going to be reduced. So nowadays the developed countries have started to reduce the use of chlorofluorocarbons, and developing countries are allowed to use to some extent, but day by day the use of CFCs is going to decrease, and it will be completely banned in few days. So this is what the impact of chlorofluorocarbons. So most of the countries have stopped the use of this chlorofluorocarbons. So 90% countries have stopped. So therefore, the use of chlorofluorocarbons is harmful to environment and hence are banned for its use. Now, this was one mistake. Instead of chlorofluorocarbons, I called yesterday as hydrofluorocarbons, HFCs. So that was the mistake in previous class. So now this is clear. Then second mistake that I committed was, so these pressure lines. Pressure lines are represented by horizontal line. So here this is the pressure line, constant pressure line, and moves along this. So this is constant pressure line. So I had explained it along this green line. So this is not a constant pressure line. So this is in this region the pressure line as well as temperature line on TS diagram. So this is a TS diagram, temperature entropy diagram. So both are going to overlap in this region, in this wet region, from saturated liquid to the saturated vapor curve. So in between this temperature line as well as pressure line are going to remain horizontal. So these are the constant pressure lines as well as temperature line up to this region, and after that the constant pressure line gets deviated and temperature line remains horizontal. One more thing, yesterday I spelled wrong is, in place of kilojoules per kg degree Kelvin, I called it as kilojoules per kg. Entropy, unit of entropy is kilojoules per kg Kelvin. So these were the two mistakes which I did in previous lecture. So here the entropy unit I called as kilojoules per kg. Actually it is kilojoules per kg degree Kelvin. So these were the two mistakes in previous lecture. Okay. So now we'll see the components of vapor compression refrigeration system. So very first device that is used in vapor compression refrigeration system. So these are the components of small refrigeration system. So very first, this black box like device is known as a compressor. This is called as a hermetically sealed compressor. So in this compressor, a motor and pump are closed within this device, and that is sealed to avoid leakage of a refrigerant. So this is called as a hermetically sealed compressor. So this is one of the device which acts as the heart of a refrigerator. So it helps to pump the refrigerant in the loop. Then second is the device known as condenser, which you used to find on the back side of a refrigerator. So these black coils are nothing but a condenser. Function of this condenser is to dissipate heat to the surrounding. So heat which is taken from the refrigerator and that is to be rejected to the surrounding. This is the main function of the condenser. So which is found at the back side. If you touch to this condenser, you will find its temperature is higher than the surrounding temperature. Then third device is expansion device or throttling valve. So where the refrigerant is expanded and the temperature as well as pressure of refrigerant is reduced so that it will absorb the heat energy. So after this expansion device, the refrigerant enters into this evaporator. You can find this component in your refrigerator at the top, so which we call as a freezer. So in this evaporator, the refrigerant absorbs heat and gets evaporated, and this is the fourth main component of a refrigerator where the cooling effect is seen. So here cooling effect that we call as a refrigerating effect is seen in this component inside this. So these if you see here, these lines are nothing but the tubes for the passing of refrigerant. It is nothing but a passage for movement of a refrigerant in this evaporator. This evaporator and condenser are nothing but heat exchangers where heat is transferred. So this device transfers heat from system to surrounding, and this device absorbs heat from system to the refrigerant. Means heat is taken by surrounding of refrigerant into the refrigerant. So if you see this block diagram, so this is a compressor. So from this compressor, the refrigerant which is compressed passes to the condenser where it dissipates heat to the surrounding with the help of air is blown to flow rate, so that the effective heat transfer takes place, and this refrigerant which is in the form of vapor gets converted into the liquid. So condensation process takes place, or phase change. Latent heat of vaporization is rejected by this refrigerant to the atmosphere Q out and gets converted into the liquid. So this liquid refrigerant is passed into the throttling valve. So in this throttling valve, the expansion takes place, and during expansion, pressure as well as temperature of refrigerant falls, and at that time, this refrigerant, when enters into this evaporator, which is in the form of liquid, gets evaporated, and this vapor of a refrigerant is then taken by this compressor. Again it is compressed, so where temperature and pressure of this refrigerant increases, and again it is passed into the condenser. When this refrigerant comes into this condenser, so its temperature is greater than ambient temperature, so that the heat flows from this refrigerant to atmosphere. So temperature of refrigerant is greater than temperature of atmosphere, so heat is rejected. So now when it is passed into the expansion valve, throttling valve, so pressure and temperature are going to fall. So temperature of this refrigerant is less than the space temperature where it is to be cooled. So heat from this space enters into the refrigerant. If these two temperatures are same, then it is impossible for heat to flow from this space to the refrigerant. So this temperature is reduced in such a way that the temperature of refrigerant is below the temperature of space. So there is affinity of this refrigerant to absorb heat, and that heat energy is taken by this refrigerant, and refrigerant gets evaporated, so thereby producing cooling effect. So now we will discuss it in detail. The very first, the device is known as a compressor. So as we know, the compressor is device which is going to compress any gaseous substance, and where by the compression process pressure and temperature of substance is going to increase. So here low temperature and low pressure refrigerant enters into this compressor, and in this compressor, by using external aid of external energy, that is work done by the motor on this compressor, and this refrigerant is compressed. So where low temperature low pressure refrigerant is compressed to high temperature and high pressure. So when the refrigerant enters through this suction valve and the compression process takes place, so this refrigerant temperature and pressure is going to increase, so that the temperature of refrigerant increases greater than the ambient temperature. So now this high pressure and high temperature refrigerant enters into the what you call condenser. So this the temperature is higher than surrounding temperature, and then it enters into the condenser. So after that it enters into the condenser. So if we want to represent this on TS diagram, so this is the point, so which is on TS diagram. Say for example, refrigerant is at this condition. If it enters into the compressor, the refrigerant is compressed adiabatically, so from point 1 to 2. So this adiabatic process is shown on TS diagram by a vertical line. So this vertical line represents the compression process, adiabatic compression. So this refrigerant which is wet refrigerant, not completely dry saturated, is compressed by a compressor, and when it becomes dry saturated, then it is discharged into the condenser. Right now we assume that the refrigerant when it enters into the compressor is wet, and when it is compressed then it becomes exactly dry saturated. So now we move to the second device which is known as a condenser. So as I told you, the refrigerant which enters into the condenser is having high temperature and high pressure. So the temperature of refrigerant is increased in this compressor in such a way that the temperature of refrigerant is greater than ambient air temperature, and the form of this refrigerant when it enters into the condenser is vapor, dry saturated vapor right now. Now coming to this second device which is known as condenser, which generally we find at the back side of fridge refrigerator, which is a tubular section, so through which a refrigerant, vapor refrigerant is passed, which is having higher temperature than the surrounding temperature. And when this refrigerant is passed through these tubes, so as its temperature is higher than the surrounding temperature, heat is rejected, Q out. Heat is rejected to the surrounding, and this vapor refrigerant gets condensed. Therefore, its name is condenser. So cooled and condensed. So next one is high pressure, high temperature refrigerant gets condensed in this condenser. Now this refrigerant while passing through condenser gives up its latent heat to the surrounding air or water. Sometimes this condenser is water cooled. At that time heat is given to the water. If it is air cooled, then it is given to the air. So when we have seen this first process 1 to 2 by a vertical line, then now this refrigerant enters at this point 2 into this condenser, and it is condensed. The refrigerant is condensed at constant pressure and at constant temperature. So pressure P is equal to constant and temperature is equal to constant. So this condensation process, so latent heat is rejected. So that is nothing but amount of heat which is rejected to surrounding is during process 2 to 3. When this refrigerant gets converted into liquid, complete saturated liquid, then it enters into the next device known as a expansion valve or throttling valve. So here the process, in this process the heat is rejected. Now coming to the next device which is known as the expansion device. So when this refrigerant enters into this expansion device of throttling valve, so at the time of entry into this expansion device, the refrigerant is in the liquid form, and which is having low temperature and high pressure. Temperature is low but pressure is high. At high temperature and high pressure it enters into the expansion device. So when it enters into the expansion device, then the pressure and temperature both are going to reduce. So high temperature high pressure refrigerant passes through the uh, throttling valve. Throttling valve is nothing but a passing of a refrigerant through a small opening. Suddenly the expansion takes place, and due to expansion pressure and temperature of refrigerant falls such that the temperature of refrigerant coming out of this expansion device is lower than the temperature of refrigerant is lower than the temperature of the space to be cooled. So here the affinity of refrigerant increases to absorb heat energy at lower temperature. So initially we have shown this process 1 to 2 by vertical line, that is compression process. Then from compression the condensation process we have seen from 2 to 3. Now when the refrigerant enters into this expansion device, so throttling process, during throttling process what we have studied in thermodynamics is enthalpy before throttling is equal to enthalpy after throttling. Now you can find here these red curves which show constant enthalpy curve. So these red lines are showing constant enthalpy curve. So the process of expansion in this device is constant enthalpy process. So this follows this path, a curve path 3 to 4. So Throttling is nothing but a constant enthalpy process during which enthalpy remains constant and pressure and temperature of refrigerant is going to fall. So when it comes to the temperature of evaporator, then the process is stopped and the refrigerant is passed into the next device known as a evaporator. So temperature of refrigerant reaches to the lowest temperature, pressure reaches to the lowest pressure. Here T is highest temperature, here temperature is lowest temperature. Here pressure is highest temperature, here pressure is lowest pressure. So after that it enters into the condenser device. Condenser device is nothing but a tubular section which has which absorbs heat energy from the space to be cooled. So this is the space to be cooled. Heat energy is taken by the refrigerant passing through these tubes. So these are the tubes of condenser, and liquid refrigerant which is entering into these tubes gets converted into vapor, or the wet liquid wet refrigerant gets converted into the refrigerant having a higher dryness fraction. So here heat is absorbed from the space by the refrigerant in this condenser. So it consists of coil pipe in which vapor refrigerant at low pressure and low temperature absorbs latent heat of vaporization and gets vaporized. So here latent heat is absorbed. So now if we see, so this was first process 1 to 2, then 2 to 3 condensation, then 3 to 4 expansion, and 4 to 1, this is the process of evaporation. So here during process 4 to 1, the refrigerant gets evaporated at constant pressure and constant temperature. This is again temperature is constant, pressure is going to remain constant. So in this evaporator, heat is absorbed by the refrigerant and it gets converted into the vapor and this vapor is nothing but more drier than this at point 4. So here heat is taken in by the refrigerant, heat in, and here heat is rejected, Q out, and during this process work is done on the refrigerant, work is done by the compressor. So these are the three important processes. So this fourth process helps us to reduce the temperature and pressure so that the refrigerant will be able to absorb heat energy into this evaporator. Sorry, this is evaporator. So this is wrongly written. Evaporator. Then it cools this space from where it absorbs latent heat. So this space is cooled by this refrigerant, thereby absorbing latent heat of vaporization. Now coming to this working of a refrigerant, now we will see. So this is point 1, we call this as point 1, this as point 2, this as point 3, this as point 4. Now let us see this process 1 to 2. So this point we call as a 1. So this refrigerant, vapor refrigerant, enters into the compressor which is at low temperature and low pressure. So when the refrigerant enters into this compressor is a vapor refrigerant at point 1, vapor refrigerant at point 1 enters into the compressor and it is compressed adiabatically to state 2, where pressure increases to very high pressure and temperature is also high. So high temperature, high pressure refrigerant, so it enters into the condenser. So here the work is done, compression work is done on this refrigerant, and when this refrigerant enters into the condenser temperature of this refrigerant is very high, pressure is also high. So when it enters into this condenser, so the temperature TH is such that it is greater than the ambient air temperature. When this refrigerant enters into the condenser, Q out amount of heat is rejected. So the condensation process takes place from 2 to say 3. So 2 to 3 is the condensation process where the refrigerant gets condensed, thereby rejecting latent heat of this refrigerant. So heat is rejected, Q out, heat is rejected, and then refrigerant enters into the expansion device, say at point 4. At point 4, refrigerant enters into the throttling wall. Sorry, at point 3, at point 3 it enters into the throttling wall. So this is the device where the refrigerant is collected, which is known as the receiver, and from this receiver it is sent to the throttling wall. So it has got a very minute function as compared with other components. Now this throttling wall is helping us to throttle this refrigerant and the pressure. So here temperature is low, sorry, at constant temperature. So this process of condensation is constant temperature. Temperature is constant, pressure is constant. At constant temperature and pressure, the refrigerant is condensed. So again here high temperature and high pressure refrigerant is coming out of this condenser, but the phase changes. Here it was vapor. Now here it will be liquid refrigerant. Liquid refrigerant comes out of this condenser and enters into this throttling wall, and after throttling at point 4, the refrigerant which comes out will have low temperature and low pressure. So the temperature and pressure both are going to reduce. So at point 4, this refrigerant again gets converted into vapor, wet refrigerant, or not completely dry saturated vapor, but it is wet. So once this expansion process takes place, so temperature is low and pressure is low. So lower temperature at this point is in such a way that it is having affinity to absorb heat energy from this cold space. So lower temperature is nothing but temperature below the space temperature or refrigerator temperature. Then the heat is taken in, so Q in, so heat is absorbed, and this refrigerant gets evaporated, or the quality of refrigerant, vapor refrigerant increases. That is nothing but dryness fraction X value. Earlier was less. Now dryness fraction gets improved, is high. So that is nothing but the vapor of refrigerant, by absorbing latent heat of vaporization, again it enters into the compressor. So when it enters into the compressor, so it has got low temperature, low pressure refrigerant. When it enters into the compressor, again work is done. So here Q in, heat is absorbed. So that Q in is nothing but net refrigerating effect produced. That is nothing but amount of heat taken from this cold space, and which is given on TS diagram by this area. So this area represents the amount of heat taken by the refrigerant, which we call as a refrigerating effect, and the work done by the compressor is given by this area. So this area gives us the work done to compress the refrigerant in a compressor. So this is how we find the working of vapor compression refrigeration system. Now looking at this diagram, we will find the pH and TS diagram. So here already we have seen point 1 is the inlet to compressor at low temperature, low pressure, and vapor refrigerant. It enters into the compressor, work is done. So this is on TS diagram. On pH diagram also, if we show point 1 here, low temperature, low pressure refrigerant enters into the compressor and it is compressed adiabatically. Adiabatic process is shown by a curve on pH diagram. So this is pH diagram. And the refrigerant when it comes out is dry saturated, for example here. So a dry saturated refrigerant at high temperature and high pressure comes out. So here high temperature and high pressure refrigerant comes out. So this is nothing but a adiabatic compression process. So from 1 to 2 we show as a adiabatic compression process. So here during this compression process there is no heat transfer from system to surrounding. So 1 to 2, we can call this as 1 to 2 is compression process during which work is done. Now from 2 to 3 there is a condensation process. So at constant temperature and at constant pressure, the refrigerant is rejecting heat into this condenser to the surrounding, and heat thereby rejecting heat, this vapor refrigerant gets converted into liquid refrigerant at point 3. So it has got high temperature, high pressure, but is liquid refrigerant. So refrigerant coming out of this condenser is liquid. So this process of condensation is shown by this line 2 to 3 on pH diagram. And again from this 3 to 4 the expansion process takes place. So expansion process 2 to 3 is condensation, and 3 to 4 is expansion process, during which enthalpy remains constant 3 to 4. So this is constant enthalpy line 3 to 4. So this is shown by process 3 to 4, say this is. So constant enthalpy process. Again this constant enthalpy process is shown on pH diagram, during which the enthalpy remains constant. So on pH diagram enthalpy on vertical line remains constant. So this is process 3 to 4, and 4 to 1 is the evaporation process. So after this this refrigerant enters into the throttling valve and it comes at point 4, which is at again low temperature and low pressure. So during expansion temperature and pressure is going to fall, where the enthalpy remains constant. So this refrigerant is in the form of vapor. Again this liquid gets converted into vapor, but having low dryness fraction. XL is low, so dryness fraction is lower. So again this refrigerant enters into the evaporator. So when it enters into the evaporator, temperature of refrigerant is such that the temperature of refrigerant is smaller than the temperature of space. So here it absorbs heat, and from 4 to 1 the process is shown, where heat is absorbed Q in, Q out during process 3 to 2. So this process 4 to 1 is shown by horizontal line on pH diagram, because this process 4 to 1 is at constant temperature and constant pressure. So this process 4 to 1 is constant temperature process and constant pressure process, that is condensation process, during which the refrigerant absorbs latent heat of vaporization and gets evaporated, and dryness fraction improves here. So always it is not like that the refrigerant at the end of compression is going to be dry saturated. Sometimes this point 2 may be beyond this. So when it is beyond this point, then we call this refrigerant at the outlet of compressor will be superheated. So that depends. So at the end of compression it will be superheated, or it will be dry saturated, or it may be wet. So depending on the condition, we have to find out enthalpy at point 2, 1, 3, 4. So in the different situations we will be studying. Now we'll see the compression process. So what this compression process is and what is happening in this compression process. So in this compression process, the vapor refrigerant at low pressure and low temperature enters into the what you call compressor, and gets compressed to high temperature and high pressure. Pressure is going to increase, which is shown by the line 1 to 2 on TS diagram, and curve 1 to 2 on pH diagram, curve 1 to 2 on pH diagram. So now during this process work is done on the refrigerant. So this work done is given by H2 minus H1, where H1 is enthalpy of refrigerant at the inlet of compressor. In kilojoules per kg. So when it passes through this compressor, enthalpy increases from H1 to H2. Let H1 be the enthalpy at the inlet, H2 be the enthalpy at outlet. So this compression process is isentropic compression process. So process 1 to 2 is isentropic compression. Work done is nothing but H2 minus H1 in kilojoules per kg. So now here enthalpy at point 1 can be obtained, H1, if the refrigerant is wet here. So it is given by HF plus of X HFG. So it is at pressure P is equal to lower pressure PL of this cycle. So at PL, whatsoever is the pressure at point 1, or we call it P1. So lower pressure, the properties are taken, HF and HFG are taken from the properties of refrigerant table, just like steam table. So the refrigerant is also having its property table. So according to that, these values are taken. So again at point 2, H2, assuming that steam, so refrigerant is dry saturated, so we write here it as HF plus of HFG. So it is at pressure P is equal to high pressure pH, that is nothing but P2. So at pressure P2, HF and HFG are taken. So when it is refrigerant is dry saturated, this is one case. If the refrigerant is wet at point 2, so this point will be somewhere here in this region. So if it is in the wet region, then it is taken as HF plus X HFG. So in place of X, we call it as X2. So this we call as X1. So X2, and again these properties are taken at pressure P is equal to pH, or that is pressure P2. So when the refrigerant is wet. Third case is H2 superheated. If this refrigerant, instead of compressing to the wet, if it is compressed in the superheated region, then it is taken as HF plus HFG plus of CPS T sup minus PS. Again properties are taken at P is equal to higher pressure pH, that is nothing but pressure P2 when steam, so refrigerant is superheated. So when refrigerant is superheated, at that time we take this third equation. So to find out H2, we are going to use three different formulas depending on the condition of refrigerant coming out of this compressor. So we know H1, we know H2, we can find out work done in the compressor by using this formula. So now coming to this condensation process, when refrigerant enters into this condenser at point 2 and comes out at point 3, so it is entering at high temperature, high pressure, and when it enters into this condenser, it rejects heat to the surrounding Q out. The amount of heat rejected is given by the difference of enthalpy from 2 to 3. So here Q out, heat rejected, is given by H2 minus H3 in kilojoules per kg. So this line 2 to 3 is shown on pH diagram here. This is the line on pH diagram, and on TS diagram we are going to show 2 to 3. So here the refrigerant rejects heat and gets condensed. So here temperature is not going to change, pressure is not going to change. At constant pressure, the phase of refrigerant from uh, vapor to liquid is changing, thereby rejecting latent heat of vaporization. So we know how to calculate H2. So H3 is equal to HF at pressure P is equal to pH, or we call this as a P3. P3 is again equal to P2. So we can take it at P3 or P2. So after this refrigerant enters into this expansion device. So when it enters into the expansion device at point 3, so the expansion takes place, and during this process the throttling process takes place. Enthalpy before throttling is equal to enthalpy after throttling. So here H3 is equal to H4. So here enthalpy at point 4 is equal to enthalpy at point 3, or else if you want to find out enthalpy at point 4, H4 is nothing but HF plus of X4 HFG. So X4 is dryness fraction at point 4, and this is taken at pressure P is equal to lower pressure PL, and that is nothing but P4, where P4 is equal to P1, because this process 4 to 1 is constant pressure process. That is, the pressure at point 4 is equal to pressure at point 1. So this process T4 is equal to T1. So temperature at point 4 is equal to temperature at point 1, because this is constant pressure as well as constant temperature process. So therefore temperature at point 4 is equal to temperature at point 1. So that what you say, expansion process on pH diagram is shown here, 3 to 4. Now after that, this refrigerant enters into this fourth device known as evaporation or evaporator. So here 4 to 1, when refrigerant, which is in the form of vapor at low temperature, low pressure, enters into this evaporator and gets evaporated. So that process is shown on pH diagram here. Now here the refrigerant absorbs heat energy Q in. So refrigerant absorbs heat energy Q in, so which we call as a refrigerating effect, RE. So this refrigerating effect is produced during process 4 to 1. So during this process, the refrigerant is going to absorb heat energy, and that is given by a refrigerating effect is given by H1 minus H4. So this can be written as sorry. So H1 we can find out as, already we have seen, HF plus of X1 HFG at pressure P1, or lower pressure, that is equal to P1, or that is nothing but equal to P4. Again H4 can be obtained as HF plus X4 HFG at again lower pressure PL, which is nothing but equal to P1, which is equal to P4. So this is how we obtain the refrigerating effect in this refrigerator. So now we want to find out the coefficient of performance. So the coefficient of performance is defined as the ratio of refrigerating effect to the work done. So here the refrigerating effect is known to us, and work done is also known to us. So from this cycle itself, it is noticed that the liquid vapor refrigerant has extracted heat during process of evaporation, that is 4 to 1, and the work is done by the compressor during process 1 to 2. Therefore the coefficient of performance, COP, we call it in short COP, of a refrigerator or refrigerating system, refrigerating effect, is defined as the ratio of refrigerating effect to the work done. So refrigerating effect divided by work done. So this refrigerating effect which we have seen is H1 minus H4 whole divided by work done is H2 minus H1. So this is UOP of a refrigeration system where H1, H2, H4. H1 is enthalpy, enthalpy of refrigerant at the inlet of compressor in kilojoules per kg. H2 is enthalpy of refrigerant at outlet of compressor in kilojoules per kg. H4 is enthalpy of refrigerant at the inlet of evaporator, kilojoules per kg. So we stop here. In next class we will be looking at some numericals on this vapor compression refrigeration system.